He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
I'm sitting with my back to the blowing wind and snow. There's Scott Base in front of me and some cracks in the sea ice next to the pressure ridges, which is where the seals come and go from under the ice. They haul out, sleep a lot. The ones that are around at the moment aren't doing very much. But there's a couple of rapidly growing pups. I think they're a few weeks old and they're already probably weigh as much as I do. And they're big roly-poly balls of lard, just blubber. When you see the Weddell seals lying around on the sea ice like this, you're only seeing a tiny part of their world. The real business goes on beneath the ice. And all I've got to give me a little glimpse of that is a hydrophone. And for that, I need a hole in the ice that I can safely work from.
Wow. I have been sitting here completely mesmerised by the Weddell Seal Symphony. All of those sounds, the space sounds, those bird calls, jungle sounds, everything is seal song. There's a background buzz of clicks and crackling. That's probably snapping shrimps. But the seals? Wow. I've never heard anything like that before. Kia ora, I'm Alison Ballance, and this is Voices from Antarctica, from RNZ. Part 6, Song of the Seals. I'm at Scott Base on Ross Island, finding out what it takes to live in and do science in Antarctica. I want to find out more about the seals. And luckily, there is a team of researchers down here working on Weddell seals as part of the Ross Sea Marine Protected Area monitoring program. One of them is marine mammal expert Simon Childerhouse. Simon, we have come out to the front of Scott Base, to an area known as the pressure ridges, where the sea ice is getting pushed up against the shore. And in front of us are 1, 2, 3, 4, about a dozen Weddell seals.
Yeah.
What are we looking at here? Males, females? What's going on?
It's hard to tell the sex actually because they're both about the same size and they don't have any kind of external features to help. But there are about 3 or 4 here with pups, which clearly means they're females. So it looks like mixed group to me. Some of the females are nursing their pups or just chilling out, resting after feeding, and then there's probably a mixture of males and non-breeding females here as well.
So obviously this is the time of year they're giving birth. How old might these pups be that we can see?
Yeah, so births are kind of September, October.
So we're in late November?
Yeah, so most of the pups here are probably between, I guess, 2 and 4 weeks old. So they're about 2/3, halfway through their lactation period, so the period where they get nursed by their mother before they get left to their own devices.
So in terms of seals, are these true seals?
Yeah, they are. Yep, so they're phosid seals, kind of different to the eared seals, otarids, which are fur seals and sea lions, which we're familiar with around New Zealand.
So visually, how do I tell the difference?
These don't have external ears, which is the main feature, but they also move quite differently. The method of movement that these guys use is they swim by moving their tail or their hind flippers side to side, whereas seals and sea lions use their fore flippers as the kind of main features of propulsion. So they paddle with the front and these guys paddle with the back.
And on land, sea lions, they sort of get up on their flippers and
Yeah.
waddle quite well. I was just watching one have a little wriggle there. These Weddell seals are a bit like slugs.
Yeah, they move like caterpillars, so they kind of gyrate along, and they're really, well, most of them are in really good conditions. They're big rolls of fat, so they kind of undulate along as they go. They don't get very fast, but they can get along.
They're big animals. They remind me of, I think there was an old skit once that somebody describing a dinosaur said they're thin at one end, thick in the middle and thin at the other end, because they got quite small heads compared to their bulk. How big actually are they?
So they grow to probably 2.5 metres long, the largest, and normally 400 to 500 kilos probably, but been reported up to 600, but they're probably giants of the Weddell seal world. But yeah, they're really round, aren't they? They've got huge rolls of fat, and these reproductive females with pups have lost a big chunk of their body weight already, so because they're feeding their pups rapidly, trying to build them up.
There's one over there just going, where?
Yeah.
Mum, I'm hungry. I know I've only just finished feeding, but...
Yeah, they always want more. In the early stages, just after birth, they can put on up to 2 kilos of weight a day because they're feeding on super high fat milk that their mums produce for them.
2 kilos a day, that's amazing. You could just about watch them grow.
Yeah, you probably could. And the mums obviously reduce in size by a similar amount, so they're rapidly depleting their fat reserves to generate milk for the young, and that's how they kind of go from newborns to being weaned 6 or 7 weeks later and at 70 or 80 kilos.
It's a pretty inhospitable place to be born, I would imagine. If on a sunny day it might be okay, but if you imagine you're a small wet pup who's just been born and you're born into an Antarctic storm, what a brutal shock going from however warm it is inside a seal, 37-ish probably. Yeah. I mean, you could be popping out at minus 37.
No, exactly, yeah, well, we have that same thought. I don't quite know how they do it, actually. So, and then, they're much smaller, so they're probably, I forget, but 10 to 15 kilos at birth, so pretty small, and they've got to maintain their body warmth and heat, and they don't have big fat reserves like their mums do for insulation.
Now, a couple of these seals have got big numbers on their back, 02 and 06. Yeah. Tell me about those.
Yeah, so we're in the second year of a 2-year program, and last year another team was down putting transmitters and video recorders on seals, and so these are 2 of our candidates from last year. Some of the seals we caught, put instruments on, and then recovered them 3 to 4 days later, and other animals were left out the whole season to try and see what they did during the winter period, which is kind of a bit of an unknown for what Weddells do in the winter.
So this year you're back down again, you're putting the same equipment on the seals?
Yeah, much the same. So we have a range of instruments, but primarily they've got a accelerometer and magnetometer, which tracks its movement underwater. You line that with a depth sensor and you can basically tell their foraging patterns in 3 dimensions, up and down and twisting and turning. And then integrated into that is a camera which we attach to their head to try and see exactly what they're eating. So the magnetometer allows us to tell when we think they're doing foraging behaviour, but we can't really ever be sure quite what they're doing until we get pictures of it. So we had reasonable success last year in getting pictures of seals feeding, primarily on silverfish.
I think they're a staple for a lot of species down here.
Yeah, I think they are.
So how do you put these tags on these seals?
Well, the first thing is we've got to sedate them, anaesthetise them, so they get an injectable anaesthetic which kind of puts them to sleep, and then that allows us pretty much to go up close to them and work with them.
And then you're sticking the instruments to the back of the seal?
Yeah, so camera on their head so we can get a view of their mouth.
Seal POV?
Yeah, exactly. And then there's one on the back, the magnetometer helps us track its movements, and then we also have a VHF radio transmitter which lets us try and find them when they're at the surface so we can recover our gear.
So you put the gear on, you are then hoping that they're going to go and forage?
Yep.
Not just hang around on shore with their pup?
No.
And then how many days are you leaving the gear on before you try to retrieve it?
They'll be coming in and out, but the instrument's memory will fill up after about 3 to 5 days, so that's our aim, to catch them about that time. And then we do a similar thing, we anaesthetise them with a small injection, a much lower dose, because all we need to do is get close enough to cut the instruments off, which are glued onto their hair, and we just kind of cut through the mesh that's glued onto them and get the instruments back. And then the mesh and epoxy will just fall off when they molt later in the year.
Now, I was reading something about Weddell seals the other day, and what was it? It was they were a record holder. Oh, that's right. They're the southernmost breeding mammal in the world.
Yeah, it's quite a good fact, isn't it?
Yeah.
So I think it's a close thing between them and killer whales, because when the ice breaks out here, the killer whales can go quite a long way south as well. But I think the Weddells just have a little bit over them because they can inhabit the cracks that go further down. But yeah, no, the southernmost mammal in the world, which is pretty extraordinary because it's quite an amazing place to live.
That pup doesn't sound like a great singer yet. I wonder when and how it'll learn. It's great to see the seal pups and their mums here. The seals had abandoned the area after Scott Base was built, and seals were being killed to feed the huskies. This summer was the first time apparently in more than half a century that a good number of Weddell seal mums gave birth to their pups in front of the base. You can lie on the sea ice and, if you're lucky, hear the seals singing below. I've heard marine biologists describe the ocean as inner space, and this has to be the most spacey of inner space. And down there I know there's a seal ballet going on, as well as a symphony. When you see them up here, they just look like big blobs. But underwater, they are living an entirely different life, where they transform into sleek, graceful, fast hunters. I asked the seal researchers if we know what these calls mean, and no, we don't. Field trainer Steve Grieve is back out doing one of his regular checkups to see how thick the sea ice is. Before you made this ice hole, the surrounding ice, how thick is it?
In this area it ranges usually between 1.4 to 1.7 this season. A lot of years it can quite easily be over 2 metres of solid, thick, hard ice. You can land a C-17 plane when it's over 2 metres thick.
I still find it amazing to think you and I are standing on water.
Yep. And it's right, this location is about 23 metres deep. So yeah, we definitely want to make sure that we're standing on some pretty solid ice, because I don't feel like going for a swim in these temperatures.
No, just actually the thought of getting in that water is very unappealing.
Join the seals down there.
They've got more blubber than we do.
Yes, significantly more. However, with the food at Scott Base, I'm getting there.
We heard a bit about sea ice in part one of Voices from Antarctica. But I want to find out more about the ice that is the seals, floor, and their sealing. And Greg Leonard and Maren Richter from Otago University are the perfect people to ask.
We're just out the front of Scott Base at the moment, standing next to a pressure ridge, which is one of the greatest local monuments around. It's where the ice shelf that's just in behind us here pushes up against the relatively thin sea ice, and it gets trapped up against the coastline here, and it buckles and forms these great pressure ridges that we're looking at the moment.
Now, they talk about how the Eskimos have 50 words for snow, and we go, well, we don't have that many, but we have a lot of words for different kinds of ice. Can you quickly give us an ice tour of Antarctica? There's the ice sheets that drape over the continent, there's the ice streams and the glaciers that flow off it, there's the ice shelves.
I would say that's terrestrial ice. It's formed from snow falling on the continent, getting compacted and flowing off the slopes, just like a river, flowing very, very slowly. And then when it comes off the land and comes afloat, that's where we call it an ice shelf or a marine ice shelf. So it's got a cavity of seawater sitting underneath those. Those generally tend to be thick. Just in behind us here, it's actually relatively thin at the edge of the McMurdo ice shelf and might be on the order of 30 meters thick. Out closer to the continent, we're talking probably 7 up to 800, maybe a kilometer thick. Whereas the sea ice, quite different, forms usually seasonally, although sometimes we get sea ice that will last a season, and we call that a multi-year ice. But what we have this season, because the sea ice broke back right to the edge of the ice shelf, we call it mostly it's first-year ice. The ice we're on, we refer to as land-fast ice. It's not that it's quick fast, it's fast as it is attached to the land, so not moving around. Further from the coast, we get into what we call pack ice, which is it's formed in the same way. It's ice forming on the ocean surface, but it's acted on by waves and winds, and it's broken up into smaller pieces, and it moves around with the waves and the currents. So those are the two main types of sea ice that you'll see around Antarctica.
Maren, can you quickly talk me through the calendar year of sea ice?
In summer, the sea ice starts melting from the top and the bottom. In Antarctica, it doesn't melt as much. What mainly happens is that at some point it gets warm and warm. It gets to sort of -6 or something, and then it starts being more brittle and mushy, and you can kind of break it up more easily. And when a big storm comes along, which is relatively frequently down here, this ice breaks up through the action of the wind and the waves into little bits. We call those ice floes. And the wind then pushes them away from the continent out into the ocean, where it then eventually does melt. That happens sort of between January, February, March. You get open water in McMurdo Sound, and as it goes back towards winter in about, I say, April, May, you start forming a very thin crust of sea ice on the top of the ocean, because the air is just so cold that it freezes the top of the ocean, and that grows thicker and thicker as the year progresses, until in August it is usually thick enough for us to drive big trucks over it. So it will be over 1 metre thick, and you can drive a piston bully or a Hagland on it and do nice science. Then it continues to grow thicker and thicker. Towards November, December, it stops growing thicker, and we start the cycle again with it going thinner and eventually breaking out.
How cold does the sea ice get in winter? Does it reflect what's happening in the air above?
It does. It's buffered by, usually around this part of the sound, there's a snow layer over the top, which is like a nice warm insulating blanket sitting over the top of the sea ice.
So the coldest temperatures I've seen in my temperature records of the sea ice go down to about -40 degrees. And the warmest you see in the sea ice is around -1.9, which is the freezing temperature of ocean. So as soon as the ocean here gets colder than -1.9, it forms ice. What I'm really looking at in my PhD is, how did it change since the mid-90s to today? Has it changed at all? Is there a trend over the years, or is it just going up and down with natural cycles, but not going in any one direction? And that is really what it looks to be doing. So what we see is that there will be years with very thick ice, in the years where the icebergs were parked outside of McMurdo Sound and kept all the sea ice trapped in here, and it could grow really, really thick. And then we've got years like this year where it's broken out by storms a lot and formed a lot later in the season, locked in a lot later, so it's thinner. But there isn't an overall trend over the years we've been looking at. This environment here in McMurdo Sound is very, very stable. That is quite unique environment, and we think that that is because it gets buffered by the ice shelf, ocean and sea ice interactions here. So you get very cold ocean water that forms when sea ice freezes, and it rejects this really, really salty brine, we call it, that sinks to the bottom of the ocean, and it has the temperature that ocean water freezes at. It then flows along the bottom of the ocean to the grounding line, which is the point where the ice sheet starts to flow out and form an ice shelf. At that point, the water will be able to melt that freshwater ice, because the freezing points are different. It will mix with the fresh water and start rising, because fresh water is less dense than salt water is. And as it rises up and gets fresher and fresher, the temperature at which it starts freezing changes. So water can actually get colder than its surface freezing point. We call that supercooling, and it snap freezes in the ocean, forming these tiny little ice crystals that float upwards towards the sea ice like an underwater snowstorm basically, and form these really, really beautiful, friable little leaf-shaped crystals underneath the ice. We call it platelet ice, and it can form a kind of mushy layer or just a skeletal layer underneath the ice, because that contributes to the sea ice growth here. The sea ice doesn't just grow through heat loss to the atmosphere, which is very variable. It also grows through heat loss to the ocean, which is quite constant in this part of the world. And we think that that might be one of the reasons why the sea ice here hasn't changed so much over the past years. It's also still quite stable in the Weddell Sea region, but we do see evidence in other places of Antarctica that we've got quite strong retreat of both sea ice and of glaciers.
How do you go about measuring sea ice?
We have a few different ways that we use here in McMurdo Sound. So we've had a site out on the sea ice that was installed a little bit later than we normally like this season due to the dynamic nature of the sea ice cover that Maren was talking about before. But this is a station that really takes the temperature of the ice. To install it, we just drill a small diameter hole through the sea ice. We install what we call a thermistor chain or a thermistor probe, which is really just a stainless steel tube about the diameter of my pinky with thermistors at certain intervals down through that, and we can take the temperature of the sea ice at different levels through it as it grows and thickens throughout the wintertime. That just goes into a data logger where we have a radio link back to Crater Hill just behind us here, and then there's a cable that runs down to the Hatherton lab here in Scott Base. And so every 6 hours we poll that station, we pull in the measurements, which we're recording at 10-minute intervals, and then once a day we can FTP that data back to a computer at the University of Otago, and that gets fed right through to a website. And so I can wake up in the morning, dial in the newest graph and see what's happening in terms of sea ice temperatures, which may sound exciting, but it's kind of like watching grass grow in the end of the day. So that's one thing we do. We also have a few other sensors there. We have a snow sensor, so we can track how the snow cover has changed throughout the wintertime. And really exciting for us, just in the last 2 years, through a collaboration with the University of Canterbury, we have an EM31 instrument. So this is an electromagnetic instrument, which is basically pulsing electromagnetic energy, and it's measuring the distance from this instrument, which is sitting in a big box on the sea ice surface, to the nearest conductive layer, which is the seawater underneath. And through work done at the University of Canterbury and international collaborators in Canada and in Germany, they've developed a model that can actually tell us not just the solid sea ice thickness, but this sub-ice platelet layer, which Maren was saying a little bit about before, really unique to this part of the world where we've got interactions between sea ice and the ice shelf in behind. And when it first forms up, it's these little platelet crystals that Maren was talking about before that kind of float up and grow and get interlocked into this really nice matrix sitting underneath the sea ice. It tends to be fragile and friable. It can move around a little bit if the currents are strong enough. And eventually the sea ice from above will grow into this matrix and solidify it. And that's where we call what we call platelet ice. And this EM31 instrument can actually work out the difference between the solid sea ice and this sub-ice platelet layer sitting underneath it. And we're quite excited about that because this is one of the first, I think, overwinter measurements of EM31 signals and trying to interpret what's going on in terms of the solid sea ice above and the sub-ice platelet layer below.
Is that sensor still out there, or have you pulled it in already?
We have just pulled it in just in the last week or so. Reason why we need it, we needed to borrow that EM31 device, put it on a sledge and tow it behind a skidoo, because some of the other things that we do is we do transect lines across the sound, and we've done these for a number of years now. And what we're trying to do is transition from knowing a lot about one spot over the wintertime and actually get a better spatial representation of how that sea ice thickness changes as we go from one side of the sound to the other, and how that sub-ice platelet layer changes. And it changes a lot because, referring back to what Maren was saying earlier about the supercooled water that flushes out from underneath an ice shelf, it doesn't do that uniformly across the sound. So we get relatively thin layers here on the eastern side of the sound, and they progressively get thicker until we hit basically the middle of that plume. And then if we were to drive far enough all the way over to the continent, we'd see that start to decrease a little bit as we get closer to that coastline.
So how thick How thick's a thin layer? How thick's a thick layer?
Yeah, a thin layer can go down almost to nothing, but more commonly maybe around a metre or a little bit less here in the eastern part of the Sounds. Getting out into the middle, we've seen in past seasons 7-8 metres thick. Gets quite challenging because the way we measure sea ice is we drill a hole, we take this weighted brass bar with a tape measure attached to it and a string so we can get it out again, and we just drop that through the hole. Really easy over here because there's nothing to impede that bar from dropping down in through the ice. When you get over to the western side of the Sound, these platelet crystals that we've been talking about, because they're loose, they can actually rise up into this hole that we've just created. Instead of trying to drop this bar through water, you're trying to push it down through a slushy, and it gets quite challenging at times just to get it down far enough to take your measurements and then get it out again.
So that's what you've been doing for the last few weeks? Driving around on skidoos and doing this kind of work?
Yes, this was my first time ever in Antarctica. It's also my first time driving a skidoo. And I got to tow the EM31 instrument, which is really challenging this year because all of these pressure ridges throughout the Sound, the ice has broken out so often and then flowed out into the ocean and then got pushed back by the next storm and jumbled all up and then frozen again and then pushed out and frozen again. So you have to navigate through these little cracks in between the big pressure ridges, and that's easy enough to do on a skidoo. But I was towing a sled that was not attached directly to the skidoo. It was on a 7-metre tether behind me. So I had to manage to do very tight turns with a skidoo, 7 metres of rope, and then a 3.5-metre long instrument on a sled, because the instrument can't have anything metal close to it. Because obviously metal conducts electricity, and a big skidoo is definitely going to be much more interesting for the instrument to see than ocean water, which is a couple of meters below it. So that's why we need that big distance between the instrument and the skidoo itself.
I'm Alison Ballance, and you've been listening to Voices from Antarctica from RNZ. Stick around for some more seal song, but first, a very big thanks to Antarctica New Zealand for hosting me and my microphones. Special thanks to Simon Childerhouse from the Cawthron Institute, Maren Richter and Greg Leonard from the University of Otago, and Scott-based field trainer Steve Grieve. You can find Voices from Antarctica, including photos, at rnz.co.nz/Our Changing World, or find us as a podcast. Just search for RNZ Our Changing World. Until next time, kia ora mai. But for now, stick around for the seals.